Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Problem 132. For the parallel pipe system shown below, each pipe is cast iron with absolute roughness of 0.26 mm. And the pressure drop P sub A minus P sub B is 20.7 kilopascals. Compute the total flow between A and B if the flowing fluid is water at 15 degrees Celsius with viscosity of 0.00116 pascal second. So I'll present two solutions here. One is by using the Moody diagram and then the Colebrook equations or Colebrook equation from the transition of flow from smooth pipe to fully rough pipe. Then the second one is by using the direct uh, Colebrook equation, which is shorter and there's no need to estimate friction factors because in the first method it is a long process because we have to estimate first the friction factors, refine the friction factors until such a time that there will be no appreciable change in the friction factors, and that's the time we end up with our solution. So the total flow is equal to the flow in pipe 1 plus the flow in pipe 2. And since these two pipes are parallel, then the head loss by principle is the same for the two. So let's evaluate for our solution the relative roughness, which is absolute roughness over diameter. So for pipe 1, 0.26 over 75, and that is 0.0035. We then locate 0.0035 in the Moody diagram, then project to the left and estimate the friction factor. So we have to project it. So this is the location of 0.0035, and we estimate friction factor to be 0.028. It doesn't matter as in your estimate if it is far from real, as long as we have an estimated initial value. It will converge when we use the Colebrook equation afterwards. So 0.028, that's F1. So F1 equals 0.028. Then we evaluate E over D sub 2, the relative roughness of pipe 2. So it is equal to 0.26 over 50, and that is 0.0052. And from the Moody chart, 0.0052. So let's just estimate 0.031 because it is above 0.03. You can also estimate 0.03 if you want, but I'll just start with 0.031. So F2 is 0.031 from the Moody diagram. Then by principle, HF1 equals HF2 because the two pipes are parallel. And for our working equation for the total flow, it is Q sub 1 plus Q sub 2. So Q equals Q sub 1 plus Q sub 2. Then HF1 is equal to HF2, and that is 20.7 kilopascals divided by 9.81, the specific weight of water. So the head loss in each pipe is 2.110 meters. We then equate this to the Darcy-Weisbach friction head loss, which is FL over diameter velocity head. So therefore, 2.11 equals friction factor 1, which is 0.028 in our estimate, length 75 over diameter 0.075 times velocity head of pipe 1. From here, we can compute the velocity, mean velocity of flow in pipe 1, estimate, and it is equal to 1.216 meters per second. Likewise, 2.11 equals 0.031 times 60 over 0.05 times velocity head of pipe 2, and the mean velocity of flow in pipe 2 is equal to 1.055 meters per second. We then compute the Reynolds number for pipe 1, diameter times mean velocity of flow times density of water 1000 over viscosity 0.00116. So diameter 0.075, velocity 1.216, density of water 1000 over viscosity 0.00116, and it is 78,621. That is turbulent. Then Reynolds number of pipe 2 is 0.05 times 1.055 times 1000 over 0.00116, and that is 45474, which is also turbulent. Then we use Coolbrook equation, 1 over square root of F equals negative 2 log of quantity E over 3.7 diameter plus 2.51 over Reynolds number square root of F to refine the friction factor this time. So 1 over square root of F1 equals negative 2 log of quantity 0.26 over 3.7 times 75 plus 2.51 over 78,621 square root of F1. So using your high-tech calculator, we can compute F1, and it is equal to 0.02875. So it improves by a little amount from this friction factor from the Moody chart. Then 1 over square root of F2 is equal to negative 2 log of quantity 0.26 over 3.7 times 50 plus 2.51 over 45474 square root of F2. And F2 is equal to 0.03266. So F1 0.02875, F2 0.03266. We then substitute these values into head loss formula. Then we can have our refined mean velocity of flow in 1, and as well as at mean velocity of flow in pipe 2. So 2.11 equals 0.02875 of 75 over 0.075 V1 square over 2G. This is now the improved V sub 1. And V sub 1 is equal to 1.200 meters per second. Then 2.11 equals 0.0326660 over 0.05 velocity head of pipe 2. So the mean velocity of flow in pipe 2 can now be refined into 1.028 meters per second. We then recompute Reynolds number of pipe 1, diameter 0.075, mean velocity of flow this time is 1.2, density 1000 over 0.00116, so it is 77586. Reynolds number of pipe 2, 0.05 times 1.028 times 1000 over 0.00116, and it is equal to 44,310. We then use Coolbrook equation to estimate or compute the new friction factors. 1 over square root of F1 equals negative 2 log of quantity 0.26 over 3.7 times 75 plus 2.51 over Reynolds number 77586 square root of F1. So F1 is equal to 0.02877. So we can now finalize this value because there's no appreciable change from the preceding friction factor 0.02875, this time 0.02877. This is the refined value. So whatever is the computed mean velocity of flow in pipe 1, that would be the final velocity. Likewise, 1 over square root of F2 equals negative 2 log of quantity 0.26 over 3.7 times 50 plus 2.51 over 44,310 square root of F2. So F sub 2 is equal to 0.03270. So it also improves. So if we round up this to three significant figures, it's 0.0327, just like this. So therefore, we can say that there's also no appreciable change in F2. So whatever is the calculated mean velocity of flow in pipe 2, that should also be finalized. So substitute into the head loss formula, 2.110 equals 0.02877, 75 over 0.075 velocity head in pipe 1. So the refined mean velocity of flow in pipe 1 is equal to 1.200 meters per second. Then for pipe 2, 2.110 equals 0.0327 times 60 over 0.05 velocity head of pipe 2. So the mean velocity of flow in pipe 2 is equal to 1.027 meters per second. So finally, we can now compute the discharge expressed in liters per second. So Q total equals pi over 4, quantity pi over 4 times 0.075 square times velocity of flow in pipe 1, 1.2 plus pi over 4.05 square for pipe 2, mean velocity of flow 1.027, then quantity times 1000. So the total flow is equal to 7.318 liters per second. So here is the second solution, which is more direct and we don't need the Moody diagram. Let's just apply the Colebrook equation right away. So since head loss is known, we can establish an equation between friction factor and velocity. From Darcy-Weisbach formula, 2.110 equals F1 times length 75 over diameter 0.075 velocity head of pipe 1. So we can establish F1 V1 square, and it is equal to 0.041398. So extracting the square root of F1 is equal to square root of 0.041398 is 0.20346 divided by V1. Likewise, so from here, Reynolds number 1, which is diameter times mean velocity of flow times 1000 over 0.00116. So Reynolds number of pipe 1 is 64655 times V1. Then we can now compute or estimate V1 substituting into the Colebrook equation. So 1 over square root of F1 becomes V1 over 0.20346 equals negative 2 log of E 0.26 over 3.7 times diameter of pipe 175 plus 2.51 over Reynolds number of pipe 1, 64655 V1, then times square root of F1, which is 0.20346 over V1. So we can cancel V1, then we can evaluate this quantity here, and we can solve for V1 right away. So V sub 1 is equal to 1.200 meters per second, which is the same as this. And this is the final value because we use directly the Colebrook equation from this relation, which is accurate from the pipe friction loss. So likewise, 2.11 equals F2 times 60 over 0.05 times velocity head in pipe 2. So we can establish an equation between F2 and V sub 2 as F2 V2 square equals 0.0344985. So extracting square root of F2 is equal to 0.18574 over V sub 2. Then the Reynolds number, diameter of pipe 2.05, mean velocity V sub 2 times density 1000 over 0.00116. So it is equal to 43103 V sub 2. We then substitute into the Colebrook equation, V sub 2 over 0.18574 equals negative 2 log of 0.26 over 3.7 times 50 plus 2.51 over Reynolds number, which is 43103 V sub 2. Then square root of f2, which is 0.18574 over v sub 2. Again, we can cancel v sub 2. We can evaluate this numerically. Then times 0.18574. Then we can solve v sub 2. And it is equal to 1.027, which is the same as this. So since v1 and v sub 2 have the same values as the first solution, therefore the discharge is also the same. So Q equals 7.318 liters per second. So I suggest that you have to apply this second solution rather than the first, because the first is lengthy, the second one is more direct and short.